Okay, so let's discuss noise analysis. So besides external sources of noise, in the circuit, the components themselves generate noise. So for example, when we have a resistor, the resistor is a source of noise. And we represent this source of noise by adding, for example, so when we represent a noise in a resistor, so what we do is we add a noise source in series with the resistor R, and so we call this, let's say, E noise here, and now this is a noiseless resistor, so it's an ideal noiseless resistor here, and all the noise in the resistor has been put into this particular source here, right? And similarly, for example, diodes are a source of noise, and bipolar transistors and MOSFETs. So all these components, they generate noise, except for a ideal capacitor and an ideal inductor. And so what we'll do in this particular discussion is look at how we carry out noise analysis in circuits, and in particular we'll focus only on noise generated by resistors here. So the noise generated by a resistor En can be written as En. So this is the RMS noise here. RMS noise here. All right, so we write it as En is 4 Boltzmann constant 4 kBt times R and times delta F here. And so all these terms, this temperature in absolute units, this is Boltzmann constant, this is the resistor value here, and this is the range over which you measure the noise. And that is because when we take a resistor like this here, the power spectral density of the noise here is a white noise here, right? Is a white noise here, and depends on, so in your circuit, the amount of noise that a resistor contributes depends on the frequency range over which we are looking at the noise. And that frequency range is often decided by, usually there are capacitors, and the system, the circuit or the system has limited bandwidth. So that ends up defining what the what delta F is for that particular circuit here. And we'll look at examples in this particular discussion here. So that's the amount of noise generated by a resistor here. And so let's do a simple analysis and find out how much noise is there in the circuit. So we'll take a simple circuit like this here, right? And we'll construct a voltage divider initially, right? And we'll simply take a simple voltage divider R here. And let's say we add some source here. This is our input. This is our Vs, the input here. And let's say this is the output here, V0. Right? So this is a circuit that is given to us. And we would like to find out, for example, how much noise is there at the output. Okay? And so let's do that. So as an example, we will take, let's say, R equal to 100 kilo ohm here. Right? So what we do is every resistor that you see here is replaced by an ideal resistor and a noise source in series with it. So let's do that. So let's build up our circuit here. And now, okay, so let's put here R here. So this is an ideal resistor R, but we'll put a noise source in series with it here. We'll call it E1 here, resistor 1, let's call it E1 here. And similarly, there is a ideal resistor now, because all the noise is taken out, and we'll put a value E2 here, right? And we'll put it here, right? And this is our output here. Okay, so we would like to find out what is the, note that E1 will be equal to 4 kT, kBt, R. And so normally, many times what happens is the range over which we measure the noise is sometimes is not written out explicitly, and so we simply we write noise in terms of, in units of volts by square root hertz here, right? Square root hertz here. So it's understood that to find out the full noise in terms of volts, we'll have to multiply by square root of the bandwidth of the system here. So E1 is square root 4 kTr, and E2 is also square root 4 kBTR here, right? Okay, so both of these values are there. And as an example, we can plug in, we have taken R equal to 100 kilo ohms, and we can calculate what is the noise that is there by putting in the value of Boltzmann constant and room temperature. And we will get a value of, both of them will turn out to be around 40.7 nanovolt by square root hertz. Right, so that's the value of the noise here. Each resistor is generating a noise, RMS noise of 40.7 nanovolt per square root hertz here. And as we said, the final value of the noise will depend on the bandwidth, and we'll add a bandwidth by connecting a capacitor a little later on here. But right now, what is the net noise at the output here? Net noise at the output. So let's calculate. So first note that noise is small. It's a linear circuit, so we can calculate the noise due to E1 at the output and noise due to E2 at the output. And both cases is straightforward to see that noise, for example, due to E1 would be equal to E1 by 2, right? So E1, because it's a voltage divider, so it will be E1 by 2 at the output. And similarly, noise due to E2 will also be equal to E2 by 2 here. So each one of them is contributing a component E1 by 2 and E2 by 2 here, right? The net noise at the output, because noise is random and each one of them is input, they add up in RMS fashion here. So the net noise will be equal to E1 by 2 square plus E2 by 2 square here, right? Because they add up in RMS fashion here. You don't add up noise in terms of magnitude, but you add it up in terms of the RMS value here. So the net noise at the output, EOT, net noise at the output, EOT will be equal to, we can see clearly that this one will be equal to E1, because E1 and E2 are the same. So basically we can take E1 out and E1 by square root 2, right? So net noise at the output is going to be equal to E0, E0 says output, and T refers to the total noise here. And if we divide this quantity 40.7, so we'll get here is 28.78 nanovolt by square root hertz here, right? So what this says is that whenever you're analyzing a circuit, in this case we have only resistors, but in other cases you can have diodes and transistors. So what you can do is you can propagate the effect of each noise component to the output, whichever is up to you to define the output. The output could be here, the output could be anywhere else, right? Wherever you would like to calculate the net noise. So you propagate the effects of each noise source to the output, and then each one of them, because they are all independent of each other, you add them up in RMS fashion here, right? So that would be the net. So we call this what we have just calculated, we will call this E0T that we just calculated, we call this the output referred noise here. Output referred noise. Now sometimes what we want is what we call as input referred noise here. Input referred noise. So the idea in this is that the circuit that we just drew, right? The circuit that we just drew here, this was our output here. And so the idea is that all the noise that is there arising due to this R and this R, we could all lump it up at the input here, right? And besides that, there are the sources and all that are there, and we can call it the EIT, the input referred noise here. So now the resistors are all noise free, all these are noise free here, and their effect has been put back in the input, and we call this as the input referred noise here. So note that we have already calculated EOT, right? And wherever, whichever place you define the input, right? This is our input here, this is the input here between here and here. Now, if you calculate the gain between the input and the output, so let's call this V in, right? So let's say V0 by V in is the gain here, right? So basically the input referred noise would be nothing but EOT divided by the gain here, and that will become EIT, right? So that will become the input referred noise of a circuit here. And so that's very convenient, because what you do is the noise generated by all the components that are there in the circuit, you propagate it first to the output here. And then what you do is, looking at the gain between the output and the input, right? You can divide it by the gain and transform the noise back to the input and say, at the input we have so much of equivalent noise at the input, right? So all the effects of, so then your circuit becomes ideal as far as the noise is concerned. And all the effects of the noise sources is all put back at the input here. So for our case, we had a value of, so gain of our circuit is nothing but 0.5, right? So input referred noise will become, so if you recall, it was 28.78 nanovolt by square root hertz, and now we divide it by the gain, 0.5 here. So input referred noise will become twice of that, which is basically equal to 57.56 nanovolt by square root hertz here, right? So that's the amount of noise that is present at the input, equivalent noise, when we have resistors of values of 100 kilo ohm here. Note that if I now reduce the resistance to, let's say from R, if we reduce from 100 kilo ohm to 1 kilo ohm, because the noise is dependent on square root, and we have a factor of 100 here, so the equivalent noise will now become equal to 5.75 nanovolt by square root hertz here. So the resistors which are of higher magnitude, they contribute more noise, because noise, as we just said, due to a resistor is equal to square 4 kTr here, times delta F, of course, is there. That's why we are writing square root hertz here. All right, so right now, so this is not the full noise that is there at the input or the output. This is still, there is a square root hertz, and you may want to calculate the net noise at the output, right? And so for that, let's add a capacitor. Let's limit the bandwidth, right? So let's take a circuit like this here, same circuit here. And let's add a capacitor here, C. And this is R, and this is R, right? So suppose, and let's excite it by some AC source here. So suppose this is our circuit here, right? And we would like to calculate, this is here, we would like to calculate the net noise of the output, and we'll call this now as V0T. So that would be the next noise. This is output, and this is net noise, and we are talking about the net voltage here. And everything is in terms of RMS. Okay, so as before, what we do is each resistor, so we can transform this into a circuit like this here first. We add a resistor, let's call this noise E1, R here, let's add a resistor R here. So now these resistors are noise-free resistors, ideal resistors here, because we have taken the noise out and we have lumped them up in these noise sources, the E2 here, and we have a capacitor here, right? We have a capacitor here, V0. Okay, and we know that E1 is E1 and E2 are basically same, because we have the same values of resistors, so it's equal to 4 kT R delta F here, okay? So as usual, what we'll do is we propagate the effects of each noise to the output here. So suppose we consider E1. Suppose we consider the impact of the noise, the first noise here. So we consider the first noise here. We look at its effect here, E1 here, and there's an R here. There's an R here, and there's a C here, right? C here, and we calculate what is the effect of the noise at the output here, okay? And what we can do is we can write down the transfer because there's a capacitor here, and so capacitor, let's do a AC analysis, will contribute in impedance 1 over j omega c here. And note that we can transform this circuit into, we can do a Thevenin's, we can do E1 by 2. We can do a Thevenin's here at this particular point here. And this transforms into R by 2. And this transforms into C here, right? So let's call this V01 because we are calculating only due to noise source 1, V01 here. So now it's easy to calculate. V01 will be equal V01. So basically we know the transfer function E1 by 2. So the transfer function of this will be equal to basically from here to here. So it will be equal to 1 over j omega c by R by 2 plus 1 by j omega c here. And so V01 by E1 will be equal to 0.5 and 1 plus j omega c R by 2. Or we can write it as 0.5 by 1 plus j f by f3 dB. Right, so let's draw the circuit again here. Let's draw the circuit. So what we are looking at is basically E1 here, and there was an R here, there's an R here, and there's a capacitor here, C, and we were calculating V01, and we calculated V01 by E1 equal to 0.5 by 1 plus j f by f3 dB. Okay, so or V01 equal to multiplied by E1. Okay, and we can similarly show that V02, you can do the analysis with respect to the second noise source. You can also see that that is also equal to 1 plus j f by f3 dB. E2, and basically E2 and E1 are the same. Okay, so what we can do is let's do the net noise here. V02 square will be equal to V01 square. They add up in our RMS fashion, V02 square here. So note that E1 equal to basically E2, right? And so this will be equal to and then that is equal to 4 kT R delta F here. So, right, so let's write this down here. So that will be equal to 4 kT R, and let's do, and they're square, so multiplied by 2 because there are 2 of them, and multiplied by 0.5 square by, let's take the magnitude of this because we are calculating magnitude here, so that will become 1 plus f by f3 dB square times delta f. Okay, so V0t square will become equal to 2 kT R, right? 4 and 0.5 square, they cancel, 2 kT R delta f by 1 plus f by f3 dB square. Okay, and f3 dB, remember, is equal to 1 over 2 pi R by 2 times C here. And now we want to calculate the net noise here, so we need to integrate over the entire frequencies here, right? So the net noise would be basically the integral of this here. So we do it integral 2 kT R, we do an integral df by 1 plus f by f3 dB square here. And the integral is straightforward. So we can write this as 2 kT R. It would be pi by 2 times F3 dB here. Note that integral of 1 over 1 plus x square. Note that we are also doing from 0 to infinity. 1 over x square 0 to infinity is equal to pi by 2. Okay. So this is there here. So let's write this down as 2 kT R pi by 2. F3 dB is 1 over 2 pi R by 2 C here, right? So let's cancel terms out. 2 goes here, and 2 and 2 go here, and pi goes here, and R goes here, and we are left with equal to kT by C. So the net noise at the output, RMS noise, V0 RMS, equal to square root kT by C. So that's an interesting result, that the net noise at the output is independent of the value of R. It only depends on the value of the capacitor here. And if we take the capacitor as 10 pF, so for example, if you construct a circuit like this with 100 kilo ohms and 100 kilo ohms here, and you try to measure the output on the oscilloscope, and oscilloscope has 10 pF capacitor here, so you'll get a net noise which is equal to V0 RMS is square root kT by C. And for 10 pF, I think it comes out to be around, let's calculate, comes out to be 20.35 microvolt. That's the amount of the noise that will be present at the output here. Right, so what we have shown you here is that in circuits, resistors are a source of noise, diodes, transistors could be MOSFETs, bipolar, they are all a source of noise, and op-amps are a source of noise, obviously, and so you can calculate the net noise present at the output by propagating the effects of the noise due to each component. And you can also take the net noise at the output and divide it by the gain, and convert that into input referred noise also. All right, so noise